Most people have no problem working with percentages, like percent composition. So most people know how to go from, let's say, a fraction. Let's just talk about percentages and parts per million, parts per billion, parts per trillion. They're all the same, essentially. And so these all refer to some kind of composition. So when, when we do composition, we usually look at percent composition. Percent composition typically is by mass, but it could also be by molecule or what we call mole. And so we'll do percent composition by mass to go. And so if we have 50 parts, this could be 50 pounds out of 100 pounds total of A out of the total. And so we could use any units here, grams, pounds, etc., kilograms, whatever we want. They just have to be the same on the numerator and the denominator. And so we just set up a fraction here. So this is the fractional composition. It's 50 out of 100, 50 parts of A out of 100 total. So 50 kilograms of A out of 100 kilograms total. Okay, to go from a fraction to a percentage, what do we do? To go from a fraction to percentage, we multiply by 100%. Now, it doesn't have to be 100 grams total. Usually when you do these, you might get 5.83 grams of A or 91.2 grams of total. The numbers aren't clean like this. I just wrote the numbers clean just to make the math easier. And that way I wouldn't have to use a calculator. And so when we convert from a fraction to a percentage, we multiply by a 100%, correct? And so what's the percentage here? The percentage would just be 50%. And then if we want to convert this into decimal form, what we do to convert this into decimal form or reconvert it into a fraction? And so we would divide by, what do we do here? We divide by 100%, is that correct? And so what we could get is we could get 50 out of 100 again, or we could go to 0.50. And this 0.50 can be converted into fractional form. For example, this would just be 0.50 out of 1 part total. Does that make sense? So you guys are all familiar with this, correct? So for parts per million, it's pretty much the same thing, except, we usually do it when the composition is very low, a low percentage. So for example, if we want to convert this into parts per million, we just multiply this by 1,000,000 ppm. But now it's going to come out a huge number. So if I multiply this by 1,000,000, that's 10 squared and the denominator 10 to the 6th. So that's going to be 10 to the 4th. 10 to the 4th is going to be 50,000 ppm. It's kind of big. So if we have a composition or concentration this high at 50%, we wouldn't want to do it in parts per million because it's too big. It's kind of a hassle working with big numbers, and it's kind of a hassle working with small numbers. We want just the right size number. Just the right size number would be like 50%. That's easy to work with. And then to go from ppm back to a fraction, we could just divide it, right? We could divide it by 1,000,000 ppm. And then we could either go fractional form, that is, if we do it in fractional form, it'd be 50,000 over 1,000,000. And then we might want to get rid of some of these zeros, in the fraction to make it a little easier to deal with. So if we eliminate some of these zeros here, we might get 50. Did I get that right? Oh, maybe I screwed up my math here. 10 squared, 10 to the 6th, 10 to the 4th. Oops, I made a mistake. 500,000. It's 50 times 10 to the 4th, which is 500,000. I screwed that up. So let me correct that. In lab, when we make a mistake, you shouldn't do this. This is in your lab notebook. For calculations, this is for raw data in your lab notebook. For calculations, you could do whatever because calculations aren't raw data. But what we don't want to do is we don't want to rub it out so it's illegible like this. Instead, in lab, what we want to do is we just want to draw a single line through an error like this. And then just rewrite it. Sorry, this is 500,000 ppm. I saw I made a mistake because when I canceled out the zeros, I wasn't getting back to 50 over 100. And so I'm going to X this out. Now, if you make a mistake on the whole page, just X out the whole page. Never rip out a page. And so this is why I'm asking for the SOM binding. It's considered very poor practice to rip a lab notebook page out of your lab notebook. And so let me redo this fraction. This is going to be 500,000 over a million. And so let's get rid of some zeros here and see if we get back to 50 over 100, which we should in this case. I got to get this taken care of here. So 1, 2, 3, 1, 2, 3, 4, 4. If we eliminate 4 zeros, then I get back 50 over 100. So it's the same concentration, you see? So 500,000 ppm is the same thing as 50%. All right, what if we want to do parts per billion? So if we have this, then we can convert. We can convert from fractional form to decimal. Decimal form is kind of a hassle for this because it's quite small. And so let's go to decimal form for this here before I move on. This is going to be point, what is it, 50, 50. Oh, actually, decimal form is not so bad, maybe, point. Fine. Oh, no, that's for percent. This would be point. This is going to be points. What would it be? I can't think right now for some reason. So let me just go ahead and do that here. 500,000 parts per million divided by 1 million is going to be 0.5. Yeah. So it's the same. 0.5. Now sig figs go, it's ambiguous here. Oops. Because as far as sig figs go, if I have 50, how many sig figs is that? We have 3 choices for the sig figs. It might be exact. It depends. Is it a hypothetical question? Hypothetically 50, then we'll say exactly 50 to keep things easy, right? Or it could be 2 sig figs. But if it's 2 sig figs, what we typically do is we put a little decimal point in here to make that zero significant. And so if I put that decimal point, then it's absolutely clear that's 2 sig figs. If there's no decimal point here, then normally I think of that as 1 sig fig or infinite sig figs. Depends. So either 1 or infinite sig figs. And so it's a little bit ambiguous, so I might be sloppy with the sig figs here, but we'll keep it at 2. So I'll do this. Yeah. All right, now the chlorine level is 1 ppm. Well, parts per billion is the same thing, If we do parts per billion, I'd not multiply by a million, I'd multiply by a billion. If I multiply by a billion, then I'm going to get 500 million parts per billion. 500 million parts per billion is the same as 50%. Does that make sense? And I could do the whole spiel. And then parts per trillion, I'd multiply by a trillion. Parts per million, parts per billion, and parts per trillion are very useful when the composition is extremely low. You have trace amounts. Like for example, I hope the lead level in our tap water is at the parts per trillion. I think the EPA designates, 4 parts per billion is acceptable. I forgot the exact number. I have to go back and look at it. And so as long as your water meets that standard, then it's they call potable water. Some things higher, some things lower, and those standards sometimes change. Okay, now we're at 1 part per million chlorine. And this is not useful for us as a conversion factor if we're going to use this as a conversion factor. So what we're going to do is we're going to just convert that into fraction. And they already told you, this is going to be 1 gram of chlorine per million grams of what? Now here is one of the things that you have to do in Chem 1A that you didn't have to do in Chem 4. And that is we have to keep track of this. So for example, in Chem 4, you might have just ignored this chlorine, Cl here, and just wrote grams over grams. Does that make sense? 1 gram is equivalent to 1 million grams? Does that make sense at all? No, it doesn't make any sense at all. So when we do these, most of the time, we do use composite units. So this is grams of chlorine here, and this would be grams of cool water here. So this would be our conversion factor that we'd use. And we can use this to convert from grams of pool water to grams of chlorine. So if I had a million grams of pool water and I wanted 1 part per million, then in that million grams of pool water, I better have 1 gram of chlorine, pure chlorine in there. And that would give me my 1 part per million chlorine in the pool water. And so I can convert from pool water to chlorine, or I can invert this. And I'm sure you're familiar with this. We can go from grams of chlorine to grams of pool water. But the trick here is we have to specify what the grams are. And that's what we have to do a lot of in Chem 1A. I know, like, some of my students from Chem 4, they came up with these algebraic equations with 0 units. And then I thought, you're not going to get very far, because if you don't keep track of the units, it's hard to get the advanced problems. And so here, if you're not the most diligent with keeping track of units, then you should change to make sure you keep track of units, because in conversion factor calculations, we need to make sure that the units cancel out. And so is this an intensive property or an extensive property? Most conversion factors are, in fact, all conversion factors are so what's the difference again between intensive and extensive? Yeah, that's exactly right. And so if we're thinking about like the conversion between liters and gallons, it's 3.785 liters per gallon. Does that change if I have 2 gallons or 35 gallons? No, it doesn't change. So those are intensive. It doesn't depend on the amount. And so here, does it matter how much pool water I have? Does this ratio change? Let's say I don't want 1 million grams. I want 500,000 grams. Will that ratio change? Not if I want 1 ppm chlorine. And so if I have 500,000 grams of pool water, then I need 0.5 gram of chlorine, and that ratio stays the same. So this is an intensive property. I think all of the conversion factors are going to be intensive properties. So this automatically for me is a conversion factor. And so I log this in my mind. Okay, this is a conversion factor I'm going to use to convert from grams of pure chlorine to grams of pool water and vice versa. All right, let's take a look at the other information that's given here. A solution used to chlorinate a home swimming pool contains 7% chlorine by mass. All right, well, that's a simple percentage. So we can go from percentage to fraction. We want fractions because fractions is what we use for conversion factors. And so let's convert a percentage to fraction. That's easy because we'll just divide by 100%. The percents cancel. That gives us 7 out of 100. Now, this is in mass, so we can put any units we want here. So this could be 7 pounds out of 100 pounds or 7 grams out of 100 grams. But since grams are the most common mass unit that chemists use, we're going to use grams automatically here. It could be ounces, 7 ounces of 100 ounces. All the ratios are the same. So we're going to go 7 grams over 100 grams. But should I leave it like this? A lot of people just leave it like that. But it's impossible to leave it like that. And so Chem 1A, we have to add what we're talking about here. It's going to be a composite unit. And the composite unit is like we did yesterday with acre and feet. We got to cancel out both or one or none, but we have to treat those as 2 units. And so this is going to be grams of what? 7 grams of what? Chlorine or chlorine solution? Okay, this is going to be chlorine solution. This is not pure chlorine, or is it pure chlorine? Okay, then what's the 100 grams? Okay, so the 100 grams will be the chlorine solution, correct? Let me back this up. Okay, what's the difference between chlorine and chlorine solution? Yeah. This 7 grams is pure chlorine. Now, chlorine is one of the diatomic elements, but and so really we should write Cl2, but actually they don't use Cl2 in chlorinating solutions. They use like bleach or something. So it would have the bleach would contain 7 grams of chlorine atoms in there, or the equivalent to that. So I'm just going to write Cl rather than Cl2. And then this grams of chlorine solution is a mixture. So in this mixture, 100 grams of this mixture, we're going to find 7 grams of pure chlorine. All right, so this is another conversion factor. So we can convert from grams of chlorine solution to grams of pure chlorine, or vice versa. And so we can just flip this the other way. But the important thing is we have to write out all the units to make sure everything will cancel properly. And then we did the 1 part per million, 1 ppm. If you assume densities of 1.10 grams per milliliter for the chlorine solution, so again, we're going to have to do this. We have this 1.10 grams per milliliter, but what is that? 1.10 grams of what per milliliter of what? Okay, when we're thinking about density, it's going to be the same thing on the top and the bottom. And so it's going to be 1.10 grams of chlorine solution per milliliter of chlorine solution. Or vice versa. I mean, 1 milliliter of chlorine solution weighs 1.10 grams. What's the density of water qualitatively? 1. So this is about 10% more dense than water, which you kind of expect because chlorine's kind of a heavy atom, right? And so it's a little more dense than just pure water. Probably you wouldn't want to drink this, of course, all right? However, take a look at the density of the pool. 1.00 grams per milliliter for the swimming pool water, which means it's close to pure water, right? Pure water is 1, roughly. Depends on the temperature, At 4 degrees C, it'd be 1. But anyway, this is just slightly more dense. Because let's say at room temperature, you know what room temperature is in Celsius? 25 degrees C. This is 77 Fahrenheit. It's a little warm. It'd be too warm for me, but that's the agreed upon room temperature. And so at about room temperature, it's more like 0.98. So this is a little bit more dense than water. If we're more quantitative, if we're more precise and more accurate, then we'd see that this is more dense, which makes sense because it's got chlorine in it. Plus, not only does pool water have chlorine, it has like other chemicals in there, chlorine stabilizers and acid, etc., maybe some base. And so this density is 1.00 grams of pool water, let's just say, per milliliter pool water. Per 1 milliliter pool water, if you want with that. Or, we'll just flip it upside down. All right, so these are all these intensive data that we're given here. And then we're given this. We want a chlorine level of 1 ppm in an 18,000 gallon swimming pool. So 18,000 gallons, is that intensive or extensive? This is extensive. 18,000, yeah, that's going to depend on the amount. And so normally when we do a problem like this, we start off with the extensive quantity first. And so if you're getting stuck, we'll just go through this. How did you guys, because I assume that you guys that calculated would have done something similar to this maybe, or if you did something different, let me know. I'm curious. But we're going to have 18,000 gallons of pool water. And the way I think about it, I mean, there are different ways I think about this. One way I think about this is, it's kind of intimidating. Like if you're going to, let's say you want to go climb Mount Everest or something, that would be pretty intimidating to do. But if you break it down into step, then or sections, then maybe each section isn't so difficult. It would just be. And so, if we think about the whole thing, it might be like paralyzing to think about because it just where do you go? Where do you start? But I just do it step by step, and I don't think about the end. I just think about gallons and pool water. So we have 2 units. We want to cancel out either gallons of pool water together, or gallons alone, or pool water alone. And so we want to cancel those out. Now, I think back, do I have anything that would cancel out both gallons and pool water? No, I don't have anything that would cancel out both, but I do have something that would get rid of the gallons. And so let's just get rid of the gallons first. That is, 1 gallon is equivalent to 3.785 liters. And so at least I got rid of the gallons. Now, I don't know if this is the correct path. What I'm trying to do is I'm trying to work my way through a jungle, and there are a whole bunch of paths in the jungle, but I don't know which one's the correct path. But it doesn't bother me. If I go down the wrong path, I don't care, because if I get stuck, I'll just go in reverse. It's like if you go down a dead-end street, you don't want to be paralyzed there and then stuck, and then somebody finds your skeletal remains in the vehicle. You don't want that to happen. If you get stuck, you back up and then try a different path. And so now we have liters of pool water. Do we have anything that gets rid of liters of pool water? No. But we do have something that gets rid of liters. We can go from liters to gallons, right? But if we go liters to gallons, then we're going in circles. And if we keep doing that, we're going to be stuck in one of those ant circles and get nowhere, unfortunately. So we don't want to go back to gallons. We want to go to milliliters. Now I have milliliters of pool water. Is there something that gets rid of milliliters of pool water? Yes. The density. The density gets rid of milliliters of pool water. And that is, the density was 1.10 grams of pool water per milliliter of pool water. And so this is, I'm sorry? What was it? Oh, yeah, sorry. It's just 1.00. This is the wrong density I'm using here. The pool water is close to pure water, which you'd expect because the concentration of the chlorine is extremely small. But you wouldn't want to drink it. But if you drank pool water, you probably wouldn't die, which would be good. Which I've done probably a bunch of times. So now the milliliters cancel and the pool water cancels, but I'm left with pool water here. But now I have grams of pool water, and either I'm going to get rid of grams or grams of pool water. Is there something that gets rid of grams of pool water together? There is something that gets rid of grams of pool water, and that is, if I have 1,000,000 grams of pool water, how many grams of chlorine do I want? 1 gram. So 1,000,000 grams of pool water needs to contain 1 gram of chlorine. To give us a level of 1 ppm. Now, the 1 ppm, that's the standard. If it's a standard, 1 ppm is the standard for, let's say, pool water. If it's a standard, then usually we treat that as exact. We'd like to get exactly 1 ppm. And so you might think, 1 sig fig, but I'm going to treat this as more than 1 sig fig. All right, now the grams of pool water are completely canceled out, and we're left with grams of pure chlorine. Now, we're either going to get rid of grams or grams of pure chlorine. Is there something that gets rid of grams of pure chlorine? Yeah. We need 7 grams of pure chlorine for every 100 grams of chlorinating solution or chlorinating mixture. All right, now how many sig figs do I have here? So let's go back up here and take a look. They say chlorinating solution contains 7%. How many sig figs would you treat that as? I might treat the 1 ppm as exact because that's probably some state standard. But the 7%, I'm probably not going to treat as exact because you're buying that from a pool supply company, right? So if you buy this from a pool supply company, then how many sig figs do you think we have here? Just 1. Because do you think the pool supply company is going to take, extra time to make sure they get it right on 7? Not at all. In fact, maybe some pool supply companies might do the opposite. It's like you hear about these pharmacists who dilute the medication. Did you hear about that? It's pretty awful that they would dilute like chemotherapy drugs for patients and then try to double their profit. But if there's some kind of unscrupulous pool supply company, they might try to go 6.5 grams because 6.5 grams would round to 7, and then they save a half a gram for every 100 milliliters, right? And so that could be a situation too. And so we don't know, are we getting, because when I see 1 sig fig, that means we're getting anywhere from 6.5 grams to about 7.4. Now, if the pool supply company said it's 7.00%, then yeah, I'm not going to worry because that's pretty precise. I don't know about their accuracy, but I know at least it's fairly precise. And I don't have to worry about overcompensating one way or the other. Because if it's 6.5, then we're not going to have enough. We probably should add a little bit extra. But anyway, the grams of pure chlorine cancel, and that gives us the grams of the chlorine mixture, the chlorine solution. And then we go to this. Is there something that gets rid of grams of chlorine solution altogether? Yes. And what was that? The density. And here I'll put in the right number. 1.10 grams of chlorine solution per 1 milliliter of chlorine solution. Now, did they ask for milliliters or liters of chlorine solution? They asked for liters? Okay. So now we're just going to get rid of the milliliters, not the chlorine solution. And so that's 1 liter is equivalent to 1,000 milliliters. And so this would give us liters of chlorine solution. And so let's see what I get. Since we had 2 conflicting answers, we try to get more answers to see, and this would be like peer review, 18,000 times 3.785 times 1,000. I'll skip the 1 and divide by 1,000,000, or 1 times 10 to the 6 times 100 divided by 7 divided by 1.1 divided by 1,000. I probably could have saved a little bit of time doing some other stuff, but I get, and then you can verify this as well, 0.8848. When we express our answer, we have to make sure we put the units here, milliliter of the chlorine solution. And then we have to round this to the correct number of 6 figs. So how many 6 figs should I round this to? How many 6 figs am I allowed if I call 7 just 1 sig fig? I'm only allowed 1 sig fig, so I'm going to round this. Oops, liters, right. Thanks. This is another benefit of the peer review process, because sometimes, when you're doing stuff, sometimes you don't see your mistakes because your mind automatically ignores it. You think you got it right, but sometimes you have. So what this means is, because of the uncertainty in this, who made that chlorine solution? How accurate is it? It's not very precise, but let's just say it's accurate. Then it's anywhere from 6.5 to 7.4. So that means we better add anywhere from 0.85, if it's 7.4, or 0.94 if it's 6.5. Does that make sense? And so the precision of our final answer kind of reflects the uncertainty here. And so therefore, when we add our chlorinating solution to the swimming pool, then we can compensate for that. All right, this itself is an advanced problem, but I made a mistake here. Do you know what the mistake was? Did anybody else get this answer here? Well, yeah. So I don't know, double check this one just to see. But anyway, there is one mistake I made. Can you tell me what it is? This would be advanced. Let's say I bought the cheap stuff. Rather than having 7%, let's say I bought the super cheap, so 7 parts per million chlorinating solution. It might not be so cheap because the shipping would be insane. If you bought 7 parts per million chlorinating solution, it'd be awful, right? Because you'd have to dump so much chlorinating solution into the swimming pool to get that level. But if you're dumping a whole bunch of chlorinating solution in the swimming pool, what's happening to the volume of the swimming pool? It's increasing. And is the volume still going to be 18,000? Or is it going to be more than 18,000? It's going to be more than 18,000. You don't have to worry about this because I'm not going to, it's just, we're making an assumption here. And we do this a lot in chemistry. We do this to simplify the math. Assuming 18,000 gallons plus 0.9 liters is about 18,000 gallons. Does that make sense? What we want to say is that the addition of a liter is not going to change the volume enough that we're going to worry about it. Does that make sense? But what if the volume change were significant? Let's say rather than adding 0.9 liters, I'm adding 1,000 gallons. If I'm adding 1,000 gallons and I'm doing my calculation based on 18,000 gallons, am I going to get the right amount of chlorine? Okay, and so this is the advanced level of problem solving. We're going to have a few of these, maybe. Actually, there are a few of these in the homework, and that is there's another way. I told you the most common way of solving chem problems will be conversion factor, but we're also going to have a number. Actually, some of these aren't so hard. We're going to have a number of system of equations. And the system of equations would just be simple: two equations, two unknowns. We're going to have a number of these, maybe about 5 or 6 of these I signed in the homework. So if I wanted, let's say, I want to be a little bit more accurate because, even with this 0.9 liters, I'm kind of feel uncomfortable, making that assumption. And so how would you have solved this without making that assumption? Well, that's two unknowns, because do you know how much chlorinating solution you have to add? And do you know what the final volume of the swimming pool is going to be at the end? No, the final volume of the swimming pool is going to depend on how much chlorine solution we add. And how much chlorine solution we add depends on the final volume of the swimming pool. And so how can we solve that? That's two unknowns, right? Two unknowns. And so we need two equations then. And then do two unknowns. So I'll just outline it here, how you would solve it. And so the volume, the pool volume is going to be 18,000 gallons plus, I'm going to call it X gallons. This is equal to the volume of the swimming pool. Which is my y. And so here are my two unknowns, x and y, the volume of the swimming pool. And so I'm going to just do substitution. I'm going to substitute this into the other equation. And the other equation is we're going to get rid of gallons and then go to liters. And then from liters, we'll go to milliliters and then et cetera. And then this is going to equal X gallons, except we're not going to go to liters at the end. We're going to go to gallons at the end. And this is going to be X gallons of chlorinating solution. So what I did was I skipped a step, and I just went ahead and plugged in this equation, y is equal to 18,000 gallons plus X. And then I plugged that in for the volume of the swimming pool, which is y. And then I changed the answer. The final answer is going to be X gallons of chlorinating solution. That's going to be the total volume. So this is going to be my one equation. And so this is not that hard, not that much harder. And so this wouldn't have been that much harder to solve as a two equation, two unknown, and then we would have been a little bit more accurate in the answer. However, if we can't make that assumption, if we can't make the assumption that X doesn't change Y, if X doesn't impact Y much, if that assumption is not valid, then we have to do this. There are going to be problems in the homework where we have to do this, otherwise it's going to be an inaccurate answer. So just be aware of that. When we hit that particular problem, then I'll tell you. This one is okay. Most chemists would go ahead and assume, if you dump a liter into a giant swimming pool, it's barely going to change the volume. Therefore, we're going to completely ignore it. Even though our answer is not going to be totally accurate, it's going to be close enough, especially since we're only at 1 sig fig. At 1 sig fig, it's already imprecise. $10.45, $10.45. Okay. Any questions on this? I'm going to move on to chapter 2 now. Do you guys like, oops, I was supposed to see that. I have to cut that out. Well, we'll just take a look.
Chapter 2 deals with atoms and atomic theory.
I think these chapter objectives are in the on the website there, Pearson. So the objectives for this chapter: describe and distinguish between the law of conservation of mass, the law of constant composition, and the law of multiple proportions. So those are three important laws. Most laws come from what? The laws typically come from two origins. Most laws come from, observations. Yeah. Most laws come from observations. Those are empirical. The other, the smaller fraction of laws comes from theory. Interestingly, two of these came from observation, and one of them came from theory. The last one. 2.2, discuss the discovery of electrons and describe the basic properties such as charge and mass. Discovery of the electrons. Do you know who was credited for discovering the electrons? Or what instrument was used in the discovery of the electron? It was a tube, CRT. CRT stands for cathode ray tube. Cathode rays were these beams, and they figured out that cathode ray beams are beams of electrons. The cathode ray tube was used to. And that, do you know the person's name that was credited with the discovery of the electron? Some names, I'm not really big on names and dates, but sometimes you'll need to know this. J.J. Thomson. J.J. Thomson. And the cathode ray tube. Describe the meaning of isotope and discuss how the masses of all elements were deduced. Well, actually, the masses of the elements were measured. Can we calculate the mass of the elements? It turns out that we can't. Do you know we know how much a proton weighs? Do you know we know how much a neutron weighs? And do you know we know how much an electron weighs? So if an atom has, let's say an atom has 9 protons, this is 9 times the mass of the proton, 10 neutrons, that would be 10 times the mass of the neutrons, plus 9 electrons. What element is that? I said 9 protons, 10 electrons, and 9, let me reverse back up. 9 protons, 10 neutrons, and 9 electrons. Fluorine, yeah, that's the element, fluorine. Did you know 100% of the fluorine atoms in nature have 9 protons, 10 neutrons, and 9 electrons? 100% of all fluorine atoms are the same. And therefore, we should be able to calculate the mass, right? Because we know the individual masses. We just multiply by 9, 10, and 9, and then just add them up. But that doesn't work. Why can't we calculate the mass of fluorine? I know what it's made of. 100% of the fluorine atoms in nature consist of 9 protons, 10 neutrons, and 9 electrons. And I know how much proton, electron, and neutron weighs. So why can't I just add up all those masses and calculate the mass of an atom? It doesn't work. It doesn't work. It doesn't work because the mass of the neutron, the mass of the proton, and the mass of the electron are all inaccurate? Or it doesn't work because of something else? It doesn't work because of something else. Is the mass of the proton, the mass of the neutron, and the mass of the electron have been measured, and those are accurate. And so, does anybody recall why it doesn't work?
they can swap electrons, but it's still going to maintain a neutral fluorine atom. I'm not talking about fluoride or any other species of ion. I'm talking about neutral fluorine. It could swap an electron, but all the electrons weigh the same. And so even if it swaps an electron, there aren't heavier electrons and lighter electrons. All electrons are the same mass. And so, so when they're talking about diffuse, this is very ambiguous. How the masses of the elements were diffused, how the masses of the elements were measured, because we aren't going to be able to calculate them. And the reason we can't calculate the mass of the electron is because of the famous mass. This is like back in chapter 2, Chem 4, I think. So it's a long time ago, especially if you had it not over the summer. Because of the mass defect. Have you heard of the mass defect? The mass defect means that the masses don't add up. Have you heard of this equation? Actually, I don't think I could break that. We have something called the mass defect. And the reason for the mass defect is because of the forces. What are the forces of nature? Do you know the forces of nature?
Gravity, electromagnetic force.
Yeah. That's good. As far as those forces of nature go, gravity, these electromagnetic forces and the nuclear forces, the weak force and the strong force. Which ones are most important to chemists? Nuclear or electrical and magnetic forces? Electrical forces are the most important. Electrical forces are the most important in chemistry. In fact, chemists don't really pay much attention to nuclear forces. There's something called the nuclear weak force. This nuclear weak force is stronger, even though they might call it the weak force. It's stronger than the electrical forces, much stronger than electrical forces. Because you guys learned that like charges attract or like charges repel. Like charges repel. So if you have 9 like charges, 9 positive charges, 9 protons stuffed into a tiny nucleus, what's holding the protons together? Is it the electrical forces holding the protons together? No, it's the nuclear forces holding the protons together. And those nuclear forces have to be stronger than electrical forces. Otherwise, the whole thing would break apart, because positive charges repel. And so what happens is some of the mass of the nucleus is converted into energy. And so the mass defect is delta E is equal to delta MC squared. So delta M is the change in the mass. So we lose a little bit of the mass of the nucleus, which is the protons and neutrons, and convert that into energy. This energy is called the nuclear binding energy, NBE. And so this is E equals mc squared, but it's delta E equals delta mc squared. C is a constant, the speed of light. And that forms the nuclear binding energy, NBE. This is not a straight proportion because some nuclei are very strong, some nuclei are very weak. These very weak nuclei form radioactive atoms, and these weak nuclei are prone to breaking apart and other stuff, prone to reaction. But when we're looking at the nucleus, how often did you look at the nucleus in high school or in Chem 4? Never, right? Other than protons and neutrons. So we aren't interested in nuclear reactions in this class. In Chem 1B, we do a little bit of nuclear reactions. In this class, we're interested in chemical reactions. Chemical reactions, the nucleus doesn't change. Even though in a chemical reaction, the atoms get rearranged, they're still the same thing. So sodium atom remains a sodium atom, even though it might lose electrons or gain or whatever, or form bonds in undergoing chemical reaction. The identity of the elements, that is the number of protons, doesn't change. And so we'll talk about this. How are atoms weighed? Does somebody remember how you weigh atoms? What instrument you use to weigh atoms? We use a mass, what? This is not working. We use a mass spectrometer, or mass spec for short. And then we can weigh atoms. Because the proportion of the mass of the nucleus depends on if it's a strong nucleus. If it's a strong nucleus that is stable, then it has a higher proportion of the mass that was converted into energy. But if it's a weak nucleus, then it's got a lower percentage of the mass that's converted into energy. So it's not a fixed quantity, and it's not easy to figure out theoretically. You would think maybe the physicists have figured it out, how to predict it, what percentage of the mass is going to be converted into nuclear binding energy. Maybe they have it all sorted out. Maybe not. 2.5, determine the atomic mass of an element from experimentally determined masses and percent abundances of isotopes. Experimentally determined masses, that's a mass spectrometer. From the weighed masses. We compile these into tables. These are called the table of isotope. We can find how much they weighed. This is just, the average atomic mass. The average atomic mass is what's given on the periodic table. 2.6, identify the different regions of the periodic table, including metals, nonmetals, noble gases, metalloids, transition metals, and main group elements. Identify the value of Avogadro's constant and describe the meaning of molar mass. And so we need to know the definition of Avogadro's number and the definition of mole and the definition of molar mass. Use Avogadro's constant to convert between values of mass. This is more unit conversion factor unit calculations. So, do you believe in the existence of atoms? Because there are two big hypotheses.
One hypothesis was that atoms exist. Atoms would be the smallest piece of matter that you could have. What was the competing hypothesis? The competing hypothesis was that matter was infinitely divisible. That is, you can take a piece of gold and break it into smaller and smaller pieces infinitely. And so, which one do you believe? Do you believe in the infinitely divisible, or do you believe in the finite limit? And that finite limit results in the smallest particle called the atom. And so I guess this is back in the, what was it, Democritus or some Greek philosophers or something. But which one do you believe in? You know, I think it was like in middle school is where I learned about atoms. And I believe in atoms because my middle school science teacher told me that matter exists as atoms. Correct? Yeah, that's the way I believe it. But in science, we don't do that because of the scientific method. Because of the scientific method, I don't know which one to believe. You know, why wasn't the other hypothesis equally as valid? If my middle school teacher told me that matter was infinitely divisible, I would have believed her and went from there. And so the question comes about is, let's say your friend doesn't believe in atoms, and they're a little bit more demanding. They want proof. And so what proof are you going to give them that atoms exist? So can you give me some proof? And so this is part of the scientific method. What type of proof do you want? What? Hmm?
Is it by adding the protons with the neutrons?
Okay, then prove to me that protons and neutrons exist.
The neutrons, both of them, and the I would say maybe it's the nuclides.
Because I've never seen a proton and I've never seen a neutron, and I need some absolute proof that they exist before I'll believe you. I don't believe. And this is science. This is. You go to scientific conferences, and sometimes you go, "Wow, that person seems so mean," but it's kind of like they're just making sure, you know, because of the way the scientific method. They aren't necessarily being mean. They just want to challenge you and make sure that you have some evidence to support whatever you're proposing. But give me some proof that atoms exist. At least give me one proof that atoms exist. Uh-huh.
Split one in half.
Have you split an atom in half?
No, we haven't.
Okay. With what? You split an atom in half with an atom smasher.
Yeah.
Okay, that's good. But when were atom smashers invented? In the 20th century, you say? Did they have atom smashers in the 18th century? Maybe with a hammer or something, you might try to smash an atom, but they didn't. We're going back to Dalton because Dalton came up with the first atomic theory in the what was it? 18th century? No, 19th century? 19th century? 20th century? 19th century. I forgot the date. 17 something. The late 1700s. So Dalton comes up with this atomic theory. Did he have an atom smasher? No. Maybe he shouldn't have called it a theory. Maybe he should have called it a hypothesis. Because maybe we couldn't call it a theory not until we got to atom smashers. But what proof would you have? Yeah, okay, what proof you have is quite a bit different than what proof Dalton had. And so what proof you have is, yeah, you could actually see these using electron or scanning tunneling microscope or scanning electron microscope. You can actually see these atoms and you can manipulate individual atoms. Like they have the IBM child, if you've seen that, or the IBM logo, which they manipulated individual atoms. And if you take these individual atoms and try to smash them into smaller pieces, they don't. They go into subatomic particles, protons, neutrons, electrons. And so nowadays the proof is overwhelming. Everybody believes in atoms because there's an overwhelming number of observations that have been observed for atoms, right? Overwhelming amount of evidence. And so if there are people who are skeptical of atoms, we have so much evidence in support of atoms that it's hard to refute. But in Dalton's times, how much evidence did he have? Did he have a scanning electron microscope, a scanning tunneling microscope? No, no. And so this is kind of what makes, if you have all these instruments and you have a ton of data, then it's easy. It's easy to make your argument. But this still happens today. I hear people say, okay, they know how this, like for example, PFAS. Have you heard of PFAS? 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 No? You guys haven't heard of PFAS? I just was listening to PFAS the other day. Somebody was talking about it. Actually, let's go back. These have been banned. These were used, this is just recently, in the last 2 years, they've been banned. But they're per and polyfluoroalkyl substances, PFAS, also known as forever chemicals. You've heard of the forever chemicals? Are a group of fluorinated chemicals. A lot of these fluorinated chemicals, like Teflon and whatever else, fluorine forms very strong bonds with things, and they're hard to break. And that makes the chemicals relatively inert, And so a lot of these were thought of as being promising for a lot of things, like, for example, weather-resistant clothing, and other like waterproof materials and food packaging and this kind of stuff. So PFAS has been completely banned from food packaging starting last year, I think. But there's still limited use because it's hard to completely eliminate it. But a 2024 study found that teas, pork, candy, sports drinks, processed meat, butter, chips, and bottled water can contribute to high PFAS levels in the human body. Now, the thing is, what does PFAS do to the human body? So I tried to look that up, and there isn't all that much information on that. The human body is very complicated. And so when some people claim that they know exactly what these chemicals are going to do in the human body, or exactly what some medication, they're going to say, they might make claims like this is totally safe. There's zero effect. You might hear claims like that in medicine. There are no side effects. You're perfectly safe taking this. Then I would start to think, it's such a complex system. What evidence do you have in support of that? If you're saying that there's no side effects and it's perfectly safe, what do you have? Well, these were thought of as perfectly safe because they're fairly inert, PFAS. But as the data come in and as new observations come in, then maybe not. I don't know. I haven't. I looked for some studies to see, but I don't know, because all of a sudden there's a big ban on it, and then things had to be checked for PFAS. And you can take a look and see if it's impacted you. But certain things are complex, and the more complex things get, the more difficult it is. And so when I think of like how PFAS impacts the body, I think about like Dalton. You think atoms. Atoms are so simple. Atom smashers, microscopes, X-rays. X-rays are great for finding atoms and picturing them. When I was working at UCSB, the group next to us, they were looking for crystals that showed a certain property. And if these crystals had this property, the way they interact with light, then they can make a lens that focuses X-rays. And if you can make a lens that focuses X-rays, then you can shine X-rays on matter and then pass them through this lens and then get a picture of the atoms. And so you can just take the picture of the atoms. But right now there's no lens, so we have to use these huge instruments called X-ray diffractometers. Let me just show you this, since we're talking about atoms right now. that does the job of the lens. And so an X-ray diffractometer, actually these are not the ones I want. Would shine X-rays, let's say at a crystal, and then scan three-dimensional space for all the light that's diffracted off the crystal, and then refocus that into an image. When you refocus it into an image, you get an image like this. The atoms don't look perfectly round here. Actually, these are just representations. You can see the contour map here, but they're a little bit oblong. They're oblong because the atoms are vibrating. You know, if you froze this to absolute zero, then they'd be spherical. You know, but you can see the vibrations in the atoms here. Since it's time average. Obviously, they want to do this for drugs, so this is pharma here. All right, let's take a break. We're going to take a 15-minute break, and then we'll start again. Sure, I'm recording here. All right, so today the evidence is overwhelming, but do you know what the evidence in Dalton's time was? I mean, how did Dalton prove the existence of atoms? What evidence did he have, or what proof did he have that atoms existed? That atoms exist? And the answer is the law of conservation of mass. Now, how do you get from the law of conservation of mass and maybe the law of constant composition to Dalton's atomic theory? And so, well, you guys know about the conservation of mass. You know, here we start off with the reactants, 104.50 grams of reactants on the centigram balance here. So the precision of this is to the nearest hundredth of a gram. And then after you mix it, we got a precipitate here, you're still left with 104.50 grams. And so that's the conservation of mass. The law, this comes from observation. So in the scientific method, we start off with observations. And it's not just one observation, it's many, many observations. Like in Chem 4, they had the burning of phosphorus and a bunch of other stuff, mercury. And here they're just showing some precipitation reaction. And so a whole bunch of people doing experiment came up with the same result. And so that was a reproducible pattern. And that reproducible pattern ended up in a law. And that law is the conservation of mass. That is delta M, mass final minus mass initial, is equal to 0. There's no change in mass. So why is there no change in mass? You know, you could be burning a candle, there's no change in mass. You could be burning phosphorus, you could do a precipitation, you could do whatever, and there's no change in mass. If you don't lose anything. Obviously, if we accidentally knock this over and all the liquid spills out onto the countertop, it's not going to be, well, it is going to be conserved, but it's not going to show the same mass. But do you have a hypothesis for this, or does it even need a hypothesis? What do you think? So if you burn a candle, you know, the candle seems to disappear, but the total mass seems to stay the same. So what were the hypotheses? One hypothesis was that there's some kind of ether, you know, and another hypothesis was these things called atoms. And so what was the evidence in support of the ether hypothesis, and what was the evidence in support of the atom hypothesis? And so the support for the atom hypothesis came like this. You know, what Dalton said was, in a chemical reaction like this, all the atoms are still there. They just get rearranged. And so they, rather than being associated with one element, they're associated with another element. And so none of the atoms were lost. And so there are no new atoms that were created, and no atoms were destroyed. And therefore, all the atoms are still there. And so this was the evidence in support of it. Now, do you believe in atoms? Is that convincing enough? Maybe not, you know, because maybe the ether, all the ether is still there. And so maybe not. So is there any other evidence in support of that, Adam? Mm-hmm.
Then is there like evidence of atoms because if you have to go infinitely, technically like matter would always be created?
Yeah, perhaps you could say something of that sort. Like, you know, if it's infinitely divisible, maybe, you know. Well, even if it's infinitely divisible, some might argue that it's still all there, you know, and so that would be in support of infinitely divisible, because even though we can divide this into infinitely small pieces, all those small pieces are still there, and we didn't lose any. So maybe that could be it. But let me tell you another piece of evidence. The other piece of evidence is the law of constant composition. So, for example, the water here, pure water, the pure water here in Los Angeles, does it have the same composition as the pure water in New York? Or is the water in New York different somehow? I'm talking about pure water. Pure water has been purified, you know. The pure water I used to use was, when I was working in the lab at UCLA, we needed extremely pure water. So the DI water wasn't pure enough. So what we did was we took the DI water, deionized water, and then doubly distilled it. And so take DI water and then distill it not once, but distill it twice. And so we call it DD water. DD stands for doubly distilled water. And then bring it through UV to make sure there's nothing growing in it. And so blast it with UV light, which is below, UV light's below 390 nanometers. And so we need wavelengths below 390 nanometers to make sure. And it depends on if you're doing near UV, which is closer to the visible, or far. You know, they have UVA, UVB, UVC, depending on how far away you are from 390. But anyway, we blasted with UV, and then it was here. But let's say you did that. If you had a glass of doubly distilled water in LA versus doubly distilled water in New York, should they have the same composition? That is, maybe water in New York has more hydrogen. Maybe it's like H3O, and water in LA is H2O, or maybe vice versa. Would you agree? Or maybe it's just slightly different. Maybe water in New York is like H2 well, New York's maybe heavier, or maybe lighter because they're faster or something. Maybe it's H2O1, and water in LA is like H1.98. What would you say? Would you say that the water in New York has more hydrogen or less hydrogen, and the water in LA has more oxygen, less oxygen? What would you say? Well, based on experiments, do you know what was found? They're the same. You know what the composition of water in New York is? H2O, and the water in LA is H2O. It's not like H3O in New York and H2O in LA. It's H2O and H2O. You know what that's called? Law of constant composition. And it could be just a little bit. What if I just had just a tiny, tiny, tiny bit of extra hydrogen in my water? Is that possible? Because, you know, I'm on a diet. I just want a little bit less of the oxygen, a little bit more of the hydrogen. Can I get it? No. You can't get it because water has a constant composition. What is the constant composition? H2O. And those are like, not like, you might say, oh, that's one sig fig. If it's one sig fig, H2 could be anywhere from 1.5 to 2.4. Do you see that for water? No, it's H2, two hydrogens, exactly. And so, and then when you do the measurements, obviously when you do the measurements, the mass ratios come out the same. So the mass of hydrogen and the mass of oxygen, which you can weigh when you break apart the water, those will have uncertainty associated with it. But anyway, it comes out very close each time. So it's H2O. That's the law of constant composition. But the situation is, if matter was infinitely divisible, then wouldn't you expect just a little bit extra? Like, say you're mixing flour and sugar. Maybe you put a little bit extra flour or a little bit extra sugar. Are you always going to get it exactly 2-to-1 ratio? If you like, let's say you like lots of sugar, you want two cups of sugar for every cup of flour. Are you always going to get it exactly the same in New York versus LA? Do you think you're going to get it exactly the same? No. And so this is another argument for atoms, because atoms have to be exactly a 2-to-1 ratio. You can't have half an atom. You can't have 1.9 atoms. You have to have 2 atoms, right, to 1 oxygen atom. And if it were infinitely divisible, then we might have an extra grain of sugar, or we might have an extra particle of flour, and therefore the water composition should vary slightly. You'd expect it to vary slightly, because each time you make water, it doesn't come out exactly the same each time. Each time you bake a cake or make cookies, does it come out exactly the same? Or, well, maybe close enough to taste, but exactly the same? No, not exactly the same. And so this is another argument for atoms. Now, do you believe atoms exist? Maybe, but maybe the evidence is more convincing or not so convincing. Have I convinced you or not really? Not really? Well, there are skeptics for atoms up until the 20th century. There are people in the 20th century that didn't believe in atoms. And so that wasn't convincing enough. But for a lot of people, that was enough evidence, because the competing hypothesis was infinitely divisible. And infinitely divisible just doesn't make sense because of just experimentally, let's say I'm going to make water. You can make water. You mix hydrogen and oxygen, and they're going to mix in ratios. I've made other things, and you make other things, and sometimes the ratio doesn't come out quite perfect. So anyway, based on his hypothesis, this hypothesis was around before. I think the person credited for atoms is probably way before Dalton. But why was Dalton credited with atomic theory? The reason why Dalton was accredited for atomic theory is because he presented it using the scientific method. He showed his proof, that is, his observations, that led to this hypothesis. Rather than earlier, there was no proof, there was no evidence for the hypothesis of atoms. And so Dalton's atomic theory is what people call the first meaningful atomic theory using the scientific method. Now, theories, they have to have widespread acceptance. So Dalton's atomic theory, more and more people started seeing the evidence and then started supporting this. But theory should do one more thing. What should theories do? Theories should be able to make predictions. And do you know what prediction was made by Dalton's atomic theory? The prediction was a law, and the law is called the law of multiple proportions. And so this is the prediction. The prediction is all compounds should be simple whole number ratios. So, for example, all compounds of oxygen and carbon should be in simple whole number ratios. So, for example, carbon monoxide, 1-to-1. Carbon dioxide, 1-to-2. And nothing in between. Versus if matter were really infinitely divisible, then you could have carbon 0.9 oxide, or 1.1 oxide, or 1.35 oxide, And so law of multiple proportions was tested, and that was what was observed. And so that was an additional thing to support the hypothesis, i.e. the theory of atoms.
How was it tested?
How's it tested? What they do is they decompose compounds into elements. How do you decompose compounds into elements? By chemical means. And so you use chemical means like electrolysis or chemical reactions, and then you can break it down. So if you had, let's say, copper, what were the two oxides of copper? Copper, does anybody remember the two oxides of copper? One is brown, the other is black. So if you have a copper penny, first it turns brown because it forms this copper oxide, and then eventually it turns black because it forms the second copper oxide. So what were the two copper oxides? Nomenclature is a lot of work. And so copper is variable charge. And when you look at the position of copper on the periodic table, and tell me the charges that are common for copper. Plus 1 and plus 2. That's good. Tell me the charge on zinc, which is right next to copper. Plus 2. Cadmium? Plus 2. Silver? Silver, Ag is plus 1. Gold? Plus 1, plus 3. Those two columns are called the pseudo group 1 and group 2 elements. And they're often labeled 1b and 2b, Roman numeral. But like things manganese, iron, cobalt, what are the typical charges of iron, manganese, and cobalt? Plus 2 and plus 3. So most of the transition elements are plus 2, plus 3, except for the copper family and the zinc family. And so the two oxides of copper are copper 1 oxides, 1 copper, 1 oxygen, and copper 2 oxide, 2 coppers and 1 oxygen. Those are the two. And so those are simple whole number ratios. So what you do is you take that copper oxide and you decompose it chemically into the elements, copper and oxygen, and then you weigh how much. And the ratio comes out to a fixed ratio. It's not a 1-to-1 ratio because the mass ratios and atom ratios are different. But we get that ratio, a consistent ratio, and then when we look at copper 2 oxide, we have twice as much copper as copper 1 oxide, and it's always twice as much, 3 times as much, etc. And so that's how you test it experimentally. You look at the mass ratios. At least this is what they did in the 1800s. What you could do now is you could do more sophisticated and then figure it out without having to do mass ratios. So anyway, all you need to know, Dalton's first meaningful atomic theory, and also where the theory came from. The theory came from observations. What observations did Dalton's theory come from? And this is the evidence in support of Dalton's atomic theory. Law of constant mass, or I don't know, what was it? Constant mass, was it? And law of constant composition, yeah. Conservation of mass and constant composition. Okay, so this is what Dalton hypothesized. Each element is composed of minute individual particles called atoms. Atoms can neither be created nor destroyed in chemical changes. We're chemists, so we don't destroy the nucleus. If we're nuclear chemists, then the nuclei, some nuclei are unstable. Those are radioactive. The nuclei break apart. But in chemical changes, the atoms don't change. They get just rearranged. All atoms of an element are alike in mass. That's false because we have isotopes. And so this is Dalton's time. It's been modified since. So modern atomic theory, we account for isotopes and other properties. But the atoms of one element are different from those of all other elements. And so atoms, even though they might be different isotopes like H1 and H2, they have the same chemical properties. Their weights are going to be different, though. In each of their compounds, different elements combine in simple numerical ratios. For example, 1 atom of A to 2 atoms of B, or 1 atom of B, whatever. This one you don't have to memorize verbatim, but that's essentially it. And so here, this is the law of multiple proportions. Simple whole number ratios, 1 to 1, 1 to 2. Carbon monoxide, carbon dioxide. How you know this is by the mass. Take a look. 1 gram of carbon, 1.33 grams of oxygen. Over here, we have double the oxygen. 1.33 to 2.66. If we had 3 oxygens, we'd have triple. 4 oxygens, we'd have quadruple. You see, that's how they figured it out. Because back then, they couldn't measure the atoms individually. All right. Again, we're not nuclear chemists, so we're not going to do so much with nuclear forces. We're dealing with electrical forces. So like charges repel, unlike charges attract. What holds the nucleus together, because you have a whole bunch of positive charges, are the nuclear forces. So this is just attraction, electrical attraction is holding this. That's what holds atoms together. That's what holds molecules together. That's what holds things together, are these electrical attractions. When we have a moving charge, it interacts with magnetic fields. And so charged particles get deflected by magnetic fields. This is electricity and magnetism. In fact, if you move the magnet, you can generate electricity, this flow of electrons. But charged particles get deflected. That's all you need to know for that. This is the cathode ray tube. The charged particles are cathode rays. Cathode rays are negatively charged particles. And these negatively charged particles are electrons, actually. They didn't know this at the time. It was J.J. Thomson who figured it out, that cathode rays are electrons. And electrons are a fundamental part of all matter. The cathode rays are generated at the cathode. We call this the cathode because the cathode, we hook it up to the cathode of a battery. And if we hook it up to the cathode of the battery, ignore the charges here. You don't need to know the charges or anything. But basically, we get a buildup of electrons over here. And this is the positive electrode here, which is called the anode. The anode on a battery is actually negative, but this is the positive one here. Or actually, no, this has got to be positive. Cathode and anode. We'll talk about that later in 1B. So you don't have to really know much about this. But what happens is electrons are generated here, but they don't flow, because there's an air gap here. But what we can do is we can generate something called a plasma. It's like these, the old fluorescent lamps, these are LED lamps now, but the old fluorescent lamps, there's no wire going through this. There's a gas in there. And what you have is an electric discharge, like a lightning bolt. A lightning bolt is one way of conducting electricity through a gas. And so what we do in a cathode ray is a controlled lightning bolt. And it doesn't look jagged. The reason it doesn't look jagged is because there's a low pressure there. A lightning bolt is very jagged because there are lots of collisions. And so as it goes down. But if this is in a vacuum here, or near vacuum, then there aren't that many things to collide with. And so the lightning bolt, and it's a controlled one, so it doesn't look so crazy, it just goes across. So cathode rays are a controlled lightning bolt in this. And basically what we do is we generate this little lightning bolt here by applying a voltage. Like voltage, about 5,000 volts is enough, or maybe 2,000 volts is probably enough, or 1,000 volts, depending on the pressure of the gas in here. The higher the pressure of the gas, the more you have to crank up the voltage. And so we get this little lightning bolt here, and then the lightning bolt's going to be attracted to this positive, but there's a hole there, and so it's just going to go over and then hit this plate back here. Now, what J.J. Thomson did was he changed the material of the cathode. He used aluminum, got the lightning bolt. He used iron, got the lightning bolt. He used stainless steel, get a lightning bolt. Use whatever material you use. You can use graphite to get a lightning bolt. The lightning bolt turned out to be the same for everything. And so what that meant was the cathode rays were a fundamental part of all matter, whether it was aluminum, iron, or steel, whatever they use for this. They always, copper is common, platinum, gold. They always got the same cathode rays. So that means cathode rays are contained in gold, platinum, copper, steel, and therefore deduce that it was contained in all matter. So cathode rays are a fundamental part of all matter because no matter what they changed the cathode to, they always got the same. And they figured that they were negatively charged particles because they were attracted to the positive plate here. And the positive plate, or you can put a piece of metal in here, and then it would gain a negative charge. You can see that. Okay, so J.J. Thomson discovered that the electrons were a fundamental part of all matter because no matter what you change the cathode to, you always got the same cathode ray, and the cathode ray were renamed electrons, electron ray. And so this is what we call an electron gun. Nowadays, you can buy an electron gun, which generates electrons and shoots them out. Now, if we bring a magnet here, charged particles get deflected by magnets. Well, they get deflected by electric fields too. So this is what we call an electric field. Electric field is we put a battery here, and then this electrons get sucked out of this plate here, making it positive, and electrons get forced onto this plate, making it negative. Now, the gap here is too hard to jump. If you crank up the voltage, then you'll have a lightning bolt between these. But if we don't crank up the voltage, then we set up what's called an electric field. And the electrons are going to be attracted to the positive. Now, if they're moving fast, if they're moving slow, they're going to go straight into that. But if they're moving fast, they'll pass it, but, they'll be attracted up. And this angle of deflection depends on how heavy it is. The heavier it is, the less it's deflected. The lighter it is, the more it's deflected. Okay, we could do the same thing using magnets. And so the electrons get deflected by a magnetic field. So nowadays we just put a magnet there. You can just put a permanent magnet. You don't have to put a battery or electricity there. And then these get deflected like this. And so the heavier it is, the less deflected because the more inertia it has. The lighter it is, the more deflected it is. And so this gives us a way of weighing things. In other words, this gives us a way of figuring out relative mass. We can figure out relative mass by the angle of deflection. And so we can see if something's heavier or lighter, depending on where it strikes our detector. This is just showing an electric field canceling out a magnetic field. You can ignore this completely. So this, I'm going to jump ahead here. Rather than shooting electrons, we shoot atoms or even molecules. If you shoot atoms, first thing you have to do is you have to charge them. So you get an electron gun and shoot. Not only can you buy electron guns, you could also buy molecular guns that shoot small molecules out or shoot atoms. And so what we can do is we could do electron impacts or molecular impacts. You get a small molecule, impact it, whatever, or electrons. Electrons are quite effective, or light. But what we want to do is we want to ionize things. And so we want to give them a charge. If you charge the atoms, this is a stream of ions. So this is a stream of positive ions. So we knock an electron off an atom, we create a positive ion. Then they get deflected. And this would be light, or would this be heavy? This atom that strikes here. Would there be a light atom or a heavy atom? Which is easier to deflect? A light or a heavy? Light. Light. Yeah, it'd be easier to deflect a light. So the lighter ones strike here, and the heavier ones are going to strike over here. Now, the thing is okay, so they strike here, so how much does that weigh? I don't know how much that weighs. How do we know how much that weighs? So what do we do if we have a balance that isn't reading correctly, or we want to make sure it's going to read correctly? What do we do to balances? We calibrate balances. And when we calibrate balances, our balances here, we buy a mass, like a kilogram mass. In the old days, there used to be a platinum palladium mass called the kilogram. Do you know where the kilogram is? France, locked in some vault there. That was the definition of a kilogram. Nowadays, it's different. They have a new definition that is available to all people, because not everybody has access to that kilogram mass. But you can buy clones of that kilogram mass. So we have clones of the kilogram mass. We walk around and we put those on the balances and make sure they're reading correctly. Right? But do you think we can feed a kilogram mass through this? Uh-huh.
You talked about deflecting and how the ones farther out are
Mm-hmm.
closer. Intuitively, I would think that the ones going farther are closer to the
Deflecting means being pulled towards a magnet. So let's say this. Let's say you have a bunch of birds flying by you and you're trying to blow them off their path. So here, if you try to blow a bird off the path, which one is going to be easier to blow off its path? Okay, so if a bird's coming this way and it's a heavy bird and you go, will it move much? It doesn't move much. And so this is trying to blow the bird off its path. You blow and it doesn't move much. It's still kind of going the same, but it gets deflected a little bit. Versus a light one. If you try to blow a light bird off the path, it gets more deflected. If it gets more deflected, do you see the angle of deflection is greater here? And if it gets deflected more, it's going to strike the detector closer because the magnet's pulling it like this because the magnetic field lines go to magnetic. We might not know about magnetic field lines, but you know the magnet has this interaction. And so that's why the lighter ones are closer here. And so, but the problem is how do we calibrate it? We can't stick a kilogram in here and weigh that, right? It's not possible. So in the old days, do you know how they calibrated it? They took an oxygen atom and they called that oxygen, in nature, do you know how many different oxygen atoms occur in nature? In nature, there are 3 different oxygen atoms or isotopes. One is oxygen 16, the other is oxygen 17, and the other is oxygen 18. So each breath of oxygen you inhale, you're inhaling 3 different oxygens, 16, 17, and 18. You can't tell the difference because chemically they're the same, but they weigh, one slightly heavier, one slightly lighter. When you had a glass of water, did you know you drank, I don't know whose water, is this somebody's water here? Would you trust it? I don't know what they put in here. Maybe it's a cleaning solution, or maybe. So if you have something like this that's unknown, you want to measure its properties, make sure it's pure, or try to separate it, make sure it's pure. But anyway, when you drink a glass of water, did you know you drank some heavier oxygen and some lighter oxygen atoms? Did you know that? Yeah. Could you taste the difference between the heavier oxygen? In other words, you drank some heavier water molecules and some lighter water molecules. Could you tell the difference between the heavier and the lighter water molecules? No. You couldn't. And the heavier ones are still so light they don't sink to the bottom. You'd think all the heavier ones would sink to the very bottom of it. Maybe in the middle of the ocean, because the ocean is very deep, maybe at the bottom of the ocean, the heavier ones would kind of settle there. And at the top, the lighter ones are there. And in fact, that's true. The heavier ones will settle. So the bottom of the ocean floor is more rich in the heavier water molecules versus lighter ones. But in the 1950s or so, what they used to calibrate the mass spectrometers was oxygen. And all they said was the lightest oxygen weighs exactly 16 U. So if the lightest oxygen weighs exactly 16 U, where it hits the detector, we calibrate it to read 16 U exactly. Does that make sense? So if you look at a periodic table from the 1950s, you have to ignore all the atomic masses because all the atomic masses are going to be off. Because do you know now we don't use oxygen 16? The reason is probably because oxygen is a gas. And working with gases is a bit more of a hassle than working with a solid. Do you know what, or liquid? Do you know what is used now? No, oxygen 16 now is weigh 15.99. Not that, that's an average of all 3 oxygens. And so oxygen 16 is actually like 15.995, I think it is. I forgot. We'll look it up. But do you know what they use to calibrate mass spectrometers now? They don't use oxygen anymore. So all the atomic masses in the old days are wrong. So don't ever buy a used periodic table from a garage sale from somebody who's retired because it's probably wrong. You're going to use not oxygen, you're going to use carbon. And carbon has 2 isotopes.
There's carbon-12 and carbon-13. Which isotope of carbon are you going to use? 12. You're going to use carbon-12. And that's good because if you have a sample of graphite, graphite's cheap. And if you have a sample of graphite, it's like 99% carbon-12. And so you put a sample of graphite here, but how do you convert it into a gas? Well, nowadays they have lasers and they do laser ablation. So you hit it with a laser and you vaporize some of the surface atoms of carbon. And what's going to feed in here are carbon-12 and carbon-13. The carbon-12 are going to land here. The carbon-13 are going to land a little bit further, correct? And then you punch in the computer where the carbon-12 hits the detector. You punch in the computer that it's not 0, but it's going to be weighing exactly 12 AMU. And so that was just chosen. Who chose it? I don't know who chose it, but somebody chose it, and that's what we use to calibrate the mass spectrometer. So we know exactly where carbon-12 hits. That's going to be exactly 12 AMU. The definition of the AMU is this. 12 AMU, atomic mass units, is defined as the mass of a single carbon-12 atom. Now, carbon-13, we can weigh it. Yeah, carbon-13 is going to weigh a little bit more, and then using some physics, we could figure it out, depending on its angle of deflection. Now, the next trick is, how do you relate AMU to grams? Okay, so we just defined a new unit. The definition of the AMU is based on carbon-12. It's the mass of carbon-12. But how do we relate it to grams? So we'll come back to that. But I wanted to go to the mass spectrometer first because it operates on the same principle as a cathode ray tube. So we have the discovery of the electron. What else do we want to know about the electron? What else do we want to know about the electron is how much does an electron weigh? And so, do you know this experiment? This is an atomizer. This thing is filled with oil. If you go to Griffith, they have one of these at Griffith. Or they had, I don't know if they still have it. But it atomizes oil into tiny droplets. And then they have a source of radiation here. They have this unstable nucleus that breaks down, shoots particles at the oil and charges them. It shoots particles at the air and creates electrons, charges these particles. And then they put it in the plate. Depending on how many electrons each drop of oil picks up, it's going to be attracted to the positive plate. And so if an oil droplet, all these are pretty homogeneous in size. So if an oil droplet grabs a lot of electrons, then it gets pulled. It could actually cancel out gravity and get pulled up. So this means electrical force is greater than gravitational force because gravitational force is pulling these down. And so if that happens, some of these will just stay stationary. That is, the gravitational force and the electrical force cancel one another out, and so they're just suspended in space. And others will just drop, but they'll drop slower, and others will drop naturally because they don't pick up any electrons. So based on this, the person who did this experiment called the oil drop experiment. Do you know who did the oil drop experiment? Millikan. The Millikan oil drop experiment, you can see one of these. And so if you look through the telescope at Griffith, you can see some oil drops that are suspended, oil drops that are being pulled up, and oil drops that are falling down. Based on that, he was able to figure out the fundamental unit of charge on the electron. The fundamental unit of charge on the electron is called C, and that's like 1.67 times 10 to the minus 19 coulombs. You don't need to know that. That fundamental unit of charge is the smallest charge we can have. And every charge is going to be a multiple of the fundamental unit. So we can have one fundamental unit of charge minus 1 point whatever times 10 to the minus 19 coulombs. 2, which would be double that. 3, which would be triple that. And so rather than calling it its actual charge, we make up a number, and we just call it -1. And so an electron has a charge of -1, which is negative 1.67 times 10 to the minus 19 coulombs, but it's much easier to say -1. Because we can have 2 electrons, which would be -2, 3 electrons, -3. And so knowing the charge on an electron and knowing its deflection in the cathode ray tube, they were able to calculate the mass of an electron using dimensional analysis. So from the cathode ray tube, we can get the mass to charge ratio. And then we have the charge. And so we multiply the mass to charge ratio by the charge, and we get the mass. And so the mass of the electron was calculated. The old days, the calculation was kind of off because the precision of the measurements and the accuracy of the measurements weren't so good. But nowadays, the mass of electrons is pretty good. X-rays and radioactivity. This has to do primarily with the radioactive isotopes. X-rays and gamma rays are high energy light, and oftentimes we see this. This come from unstable nuclei. Unstable nuclei are high energy, and when they decay, they go to lower energy products. But energy is conserved by the first law of thermodynamics, and so X-rays and gamma rays might be a product of that. Or some nuclei are so big, they're unstable. Chunks of nuclei break off. These chunks are called alpha particles, some of them chunks. And there could be bigger chunks than alpha particles, but alpha particles are a common chunk of nucleus that breaks off. And this chunk of nucleus consists of 2 protons and 2 neutrons, no electrons. 2 protons and 2 neutrons. 2 protons is the element helium, so we call them He2+. Those are alpha particles. Alpha particles are quite dangerous. X-rays and gamma rays are also very dangerous. Both of these we call ionizing radiation. X-rays, gamma rays, alpha particles. Beta particles are lower in energy. Beta particles are electrons. But beta particles, these electrons are very weird because of the origin of the electron. Beta particles are electrons that come from the nucleus. And how many electrons are contained in the nucleus? How many electrons are contained in the nucleus? None. And so how can a nucleus spit out an electron? How a nucleus spits out an electron is by a nuclear reaction. One of the nuclear reactions is where a proton decays into a neutron. When a proton decays into a neutron, it spits out an electron. And so that would be, but once it spits out an electron, you can't tell the difference. Does this electron come from the nucleus or did it come from an orbital? You can't tell. The energy might be high, though, of course. There's a beta ray. To protect yourself from gamma and X-rays, you need, for X-rays, you need lead sheets. So if you go to the dentist or something, they're going to put lead sheets, or if you break a bone, they'll put lead sheets to protect you from X-rays. To protect you from gamma rays, you need lead bricks. Lead bricks should be able to protect you. What do you need to protect you from alpha particles? To protect you from alpha particles, you just need a sheet of paper. So what's more dangerous, alpha particles or gamma and X-rays? You know what I'd rather be exposed to? Maybe gamma and X-rays rather than alpha. Alpha particles cause a lot of biological damage. And so even though you can protect yourself with a piece of paper, that's if you inhale alpha particles, because helium is a gas, it can cause a lot of damage there. Actually, I'd rather not be exposed to any of these. X-rays and gamma rays are quite penetrating as well. Beta particles, you can protect yourself with aluminum foil. But why am I talking about X-rays and radioactivity? Because of some of these experiments require that. So if you have the radioactive material here, sometimes there's some nuclear decay that spits out electrons from the nucleus. These are the beta particles, protons converted into neutron. Or sometimes chunks of the particle breaks off. Those are alpha particles. Or sometimes gamma rays. Gamma rays aren't deflected by electric and magnetic fields here. And so you can easily tell the difference between beta, alpha, and gamma rays depending on how they're deflected by the field here. There's beta particles are negative, alpha particles are positive, gamma rays are neutral. Well, some of this, you don't have to know this that much, but one of the most famous experiments, so we have 3 experiments that are pretty well known that you should kind of try to remember. J.J. Thomson, cathode ray tube, electron. Millikan oil drop, the charge on an electron. And this one, this is called the Rutherford gold foil experiment. Does anybody remember the Rutherford gold foil? Rutherford gold foil, you have a source of alpha particles here, radium, it's radioactive, so chunks of the nucleus break off, spitting out alpha particles. These alpha particles, most of the alpha particles go straight through the gold foil, but some of them are deflected. And so most of them go through. There are two competing hypotheses for the structure of the atom. One hypothesis was the plum pudding model. Do you guys remember the plum pudding model? Maybe, maybe not, because plum pudding model has been pretty much abandoned. It's been abandoned because there wasn't any supporting evidence for it. The supporting evidence was for the nuclear atom model. And what was the supporting evidence for the nuclear atom model? It was the Rutherford gold foil experiment. In the Rutherford gold foil experiment, most of the alpha particles went straight through, meaning the atom consists mostly of empty space. Because alpha particles are positively charged, and so they might be deflected or interact with the atom, but they didn't interact at all, so they just went straight through. That means they're empty space. Some were slightly deflected, so the ones that were slightly deflected could go close to the nucleus. The nucleus is positively charged, the alpha particle is positively charged, and they can be deflected. Some were highly deflected. The ones that were highly deflected must have went straight into the nucleus. If they went straight in the nucleus and bounced off, it would be like hitting a brick wall. But it's not like hitting a brick wall, because what it is positive, positive. What do positive do? They repel. And so you're trying to force a positive into a positive, and they're going to repel. Now, nuclear chemists, what they want to do is they want to force it with so much speed, so much energy that they fuse together. And that would be called a fusion reaction. So if they can get the alpha particle to actually not bounce off, but stick, that is, they need it to go so fast, therefore they're using a cyclotron to accelerate, or a particle accelerator or something, to get it so fast that it fuses and sticks to the nucleus, and they create a new atom. That's nuclear synthesis. But here they aren't going so fast. They're not going to stick. They're just going to bounce off. And these ones are the ones that bounce off. And so this was the experiment. So 3 critical experiments at the beginning. And that is the scattering of alpha particles by metal foil, which is the gold foil, Rutherford gold foil experiment. This is the plum pudding model. And the evidence didn't support it. The observations didn't support it. This is the nuclear atom model, which the atoms support. In the nuclear atom, the nucleus contains the protons and neutrons. And the atom consists mostly of empty space in which we have the electrons out here. So we talked about the discovery of the electron, which is J.G. Thomson. And then Rutherford discovered the protons. This is the same Rutherford as the gold foil experiment. And Chadwick discovered the neutrons. But we're not going to talk about these. If you're interested in the discovery of the protons and neutrons, you can read about Rutherford and Chadwick here. We're just going to skip that. This is enough history for the development. And so this is the modern data for this. We know how much a proton weighs. How much does a proton weigh? It weighs 1.0073 U. This is the U, or AMU. I call it AMU, atomic mass unit, or you could call it U, the atomic unit of mass. Note that they don't weigh exactly 1. Is there anything that weighs exactly 1 U? There is something that weighs exactly 1 kilogram. What is it? The thing that weighs exactly 1 kilogram is actually a physical object that weighs exactly 1 kilogram, and it's a platinum palladium chunk of metal sitting in a vault in France. That weighs exactly 1. But is there something that weighs exactly 1 U? No, there isn't. However, there is something that weighs exactly 12 U. What is it that weighs exactly 12 U? Carbon 12, a single carbon 12 atom. And that's how this scale was defined, the U scale. The U scale is there's nothing that defines 1 U. There's something that defines 12 U. And so based on carbon 12 weighing exactly 12 U, the proton weighs this much, the neutron weighs this much. Which one weighs more? The neutron weighs slightly more, very, very slightly more. But most people ignore it and just qualitatively say the proton and neutron weigh about the same. And how much does a proton and neutron weigh qualitatively? 1U. Uh-huh. No, you don't. The question is, do you need to memorize this? No, you don't need to memorize. The only thing that you have to memorize is qualitatively the proton and neutron weigh about 1U, and the neutron is just slightly heavier. That's all you need to know. Just like qualitatively, I don't, you don't have to be quantitative on the density of water, but qualitatively, the density of water is 1 gram. If you wanted to be more quantitative, then you got to look it up in a table, 1, or use the graph, 2, or 3. The third method of determining the density of water quantitatively would be 3. Use the law of the density of water. The law of density of water was that an empirical or theoretical law? That was an empirical law, and that was the empirical equation. In fact, I think I have a homework problem in chapter 1 or chapter 2 with that. Okay, now how do we relate U and grams? It's easy. Do you know the conversion for U to gram? Or grams to U? Yeah. The relationship turns out to be pretty easy, and you're on the right track there, basically. Maybe I'll talk about the relationship, but somehow we need a conversion factor. We need the conversion factor to go from grams to U. The conversion factor is super easy to remember because do you remember Avogadro's number to 4 sig figs? I'm just going to write the conversion factor here. What was Avogadro's number to 4 sig figs? 6.022 times 10 to the 23rd. Yeah, you remember that? Then you know the conversion factor. There's 6.022 times 10 to the 23rd U in a gram. So there's an Avogadro's number's worth of U in a gram. And so to convert from U to gram is easy. We just use that. Now, the tricky part is, where did that conversion factor come from? And the conversion factor came from the definition of the mole, M-O-L-E, the mole. So we'll talk about that later. Where did the charge on the electron, what experiment was used to determine the fundamental unit of charge? It was not 1.67, 1.6022. 1.67, where did I get that? From some other constant. Negative 1.6 times 10 to the minus 19 coulombs. C stands for coulombs. This came from the Millikan oil drop experiment, but it's too much hassle saying this. So rather than saying this, we call it negative 1. Negative 1 charge means negative 1.6022 times 10 to the minus 19 coulombs. Does that make sense? But normally we just say negative 1 charge for the electron, and the proton would be the opposite, positive 1 charge here, because it's lost an electron. Or no, that's not. It's just the opposite charge. U is the SI symbol for the atomic mass unit, abbreviated as AMU. I'm sorry? To avoid confusion. It's easier to go in multiples because then you'd have to go, if you did in multiples of 2, it'd just go 2, 4, 6, 8. And then you might start thinking, what happened to 1 and 3? In this way, it's comes in these levels. You can have 1, 2, 3, 4, and so it just makes sense in counting numbers, not to go by 2s, but to go by 1s, especially if you only have 1 electron. If you have 1 electron, we'll just say negative 1. So they didn't round this. It's just 1 fundamental unit of charge. So atoms consist of protons, neutrons, and electrons, and
atoms of different elements are different. And what's different is the composition. And so when we look at the composition of an atom, we can get it from this. So we have the symbol of the element, E, which is either 1 or 2 letters. And then we have Z. What's Z called? The atomic number. And A is the mass number. But is the mass number a mass? The mass number is not a mass. The mass is the number of protons plus the number of neutrons. Now the situation is the electron. The electron weighs about 1,850 times less. When we look at the mass of the electron, it's orders of magnitude smaller. Do you see it? And so the electron doesn't weigh much. The electron is very light. And so what do we want to know about the electron? We want to know how much it weighs. We want to know its charge. And what else do we want to know? We want to know its size. How big is an electron? How big is an electron? Well, let me back up and tell you about the size of a proton. You know, the size of a proton is about 10,000 times smaller than the size of the hydrogen atom, let's say. You know, about 10,000 times smaller. The size of the nucleus is about 10,000 times smaller than the size of the atom. So the atom's like this big, the nucleus is 10,000 times smaller. So people do these analogies. So for example, if the atom is a football field in size, then the nucleus would be how big? I mean, what would be comparable? So if the atom is a football field, then the nucleus would be like the a football. I mean, a nucleus would be like a football, or a softball, or a baseball, or a golf ball. I think it's, if the atom were a football field in size, then the nucleus would be like a golf ball, something like that. There are other analogies, things that you could think of. But anyway, the nucleus is very small. So how big is an electron? The size of the nucleus has been determined. The size of an electron, do you know how big an electron is? It's got to be really small, right? It doesn't weigh much. But do you know? If somebody tells you the size of an electron, it's kind of weird. How big is an electron? It has 0 size. Electron has 0 size. How can an electron have 0 size? And so electron is a bit strange to think about because it has 0 size. So anyway, the size of an electron is 0. We'll come back to the electron later, but it's just to tell you that the electron is a strange entity. But anyway, we can figure out how many electrons we have based on the charge. The charge here is shown in the upper right. They didn't show it here, but the charge is usually labeled like X or something like that. And it could be positive or negative, depending on, or 0, depending on how many electrons it has. So if we have the same number of protons and electrons, then the charge is neutral. But if we have different charges, then we have ions. So that's the thing that's missing here. But this is familiar stuff, right? This is a review. Okay, good. So this is mercury. One thing we want to know is how many different isotopes of each element. So mercury has how many isotopes? Count them. 1, 2, 3, 4, 5, 6, 7. So if I take a sample of mercury, vaporize it, and then feed it into a mass spectrometer, I get 7 strikes on this. Is that something you're going to predict it easily? In order to predict that, this is observation, but could you predict it? Okay, mercury has 7. How many does cadmium have? How many does lead have? How many does carbon have? How many does fluorine have? Is that something that's easy to predict? No, and so this is why we want to know the theory. If we understood the theory, then perhaps we could predict this. Not only how many,
but how abundant are they? So when I look at the lightest isotope weighs around 196 U, about one. Actually, this is extremely precise. We can get 6 to 9 sig figs after the decimal. And so we can pinpoint that mass to extreme degree of precision, extremely high degree of precision. And so the masses here we can get precisely, but not only that, do you see the peak heights? The peak heights depend on how many strikes we have. So let's say 100 strike here and 500 strike there, and we can get the relative, what we call natural abundances. So if we add up all these peak heights, that's 100%, and then we take the percentage of each of these, we get the percent natural abundance. So all these add up to 100%. And so this is the relative number of atoms that we can do, and we can calculate a percentage based on that. But which one of these is the most abundant? It looks like the one at 202 is the most abundant. So this would be like what we call a mercury 202 isotope. It's going to have a mass around 202. Its mass number should be about 202 because the protons and neutrons make up the bulk of the mass of the atom. And so this is it here. This is the most abundant. What's the average mass? Well, the average mass is not a straight average. The average mass we weight depending on how big each peak is. And so the average is going to be closer to 202 because that's where the biggest peak there is. And what's given on the periodic table is the average mass. It's 200.59. So the average mass is 200.59, which is about here. And so all these are going to balance out to about here in terms of average. Do you see that? Is there a mercury atom that weighs 200.59? No, that's just the average. So the mass spectrometer is a very powerful tool because the mass spectrometer tells us we can't predict how many because we don't know the theory. So, I mean, I don't know the theory. Maybe the theoreticians can predict how many. I'm not sure how accurate their predictions are. But we aren't going to predict it. We're just going to measure it. So the mass spectrometer measures 3 things. The mass spectrometer measures the number of isotopes, the percent natural abundance of each isotope, and the precise mass of each isotope. And we compile this data into data tables. For example, this is in Appendix D of our book. So in data table Appendix D, we have this isotopic masses and their abundance. So when we get a hydrogen, there are 3 isotopes of hydrogen. Hydrogen 1, hydrogen 2, hydrogen 3. All these have the same Z, so they don't bother writing the Z here. Z is 1. The mass number changes. So this has no protons, one proton, no neutrons, 1 neutron, 2 neutrons. And so this is heavy hydrogen here. So if we fed hydrogen in the mass spectrometer, we're going to get 2 or 3 peaks. Possibly 3 peaks because tritium, take a look at this percent natural abundance. Percent natural abundance has a line through it. And that line means it's not really abundant naturally. And the reason it's not really abundant naturally is because tritium is radioactive. It's unstable. So the 2 naturally occurring isotopes of hydrogen are hydrogen 1 and hydrogen 2. Hydrogen 2 weighs about twice as much as hydrogen 1. You can see it here. Not exactly, but close to it. And when we look at the percent natural abundance, hydrogen 1 is much, much more abundant. So let's convert this to a million. If I had a million hydrogen atoms, 999,885 would be hydrogen 1, and 115 would be hydrogen 2. And so when you have that glass of water, if you drank a million hydrogen atoms, then you just drank 999,885 hydrogen 1s and 115 hydrogen 2s. Could you taste the hydrogen 2s? No, you couldn't taste the hydrogen 2s. So we have this data table like this, where we can get the precise mass and the abundance. Now let's take a look at carbon's entry here. Carbon 12 weighs what? That's a lot of sig figs. How many sig figs is that? Carbon 12 weighs 12.00000 U. How many sig figs is this? 8? It looks like 8, but 8's incorrect. How many sig figs is it? It's infinite. Why is it infinite sig figs for carbon 12? Because it's exact. It's by definition. So carbon 12, this is how it's defined. So this is exactly 12U. And everything else is 8 sig figs. Excuse me. So carbon 13, this is 8 sig figs because this was measured. Carbon 14 is radioactive, so that's why its percent natural abundance is nil here. And so there are two naturally occurring isotopes of carbon 12 and carbon 13. So we're going to do a little exercise here. And the exercise is going to we're going to think about all the water molecules you drank today. And so we're going to take a look at oxygen. If we fed oxygen, it used to be oxygen 16 was exact, but now it's not. Oxygen 16 is now relative, it's weighed 15.9949. In the old textbooks, oxygen 16 is exactly 16U by definition. They just changed the weighing standard for mass spectrometer. But anyway, there are three oxygens: oxygen 16, oxygen 17, oxygen 18. Which one's the most abundant? Oxygen 16. So if I had 100,000 oxygen, 99,757 would be oxygen 16, 38 would be oxygen 17, and 205 would be oxygen 18. Correct? Yeah. Okay, so the most abundant is 16, the next would be 18, and the least abundant would be 17. And so this is what I want you to do. I want you to make water. How do we make water? We combine oxygen and hydrogen in what ratio? We combine oxygen and hydrogen in a certain ratio. And I'm going to this here. And we'll end today with, actually, I guess we are going to end a little sooner than that, but we're going to make water hypothetically. And to make water, we need 2 hydrogens and 1 oxygen. And then we're going to take it from the grab bag. So if I had 1 million hydrogens, most of them are hydrogen 1s, and a few of them are hydrogen 2s. Hydrogen 2 gets a name, common name, deuterium. And then if I had 100,000 oxygens, 999,000 would be oxygen 16. And then oxygen 17 would be like 38 of them. And then oxygen 18 would be like 205 of them. And so we're going to put all these atoms together and make water molecules. And so I'll make the one, if you just grabbed it, a hydrogen, which one do you think you're going to grab? An H1 or an H2? If I just grabbed a hydrogen, most likely it's going to be an H1. H2 are very rare. And if I grabbed an oxygen, which one do you think it's most likely going to be? An oxygen 16. And if I grab another hydrogen, most likely I'm going to grab a hydrogen 1. And this is going to have a mass of about 18U. This is going to be the most abundant water. And so when you had a glass of water, most of it contained H1, O16, H1. But there are other water molecules that you drank. So can you tell me all the water molecules that you can make from these atoms, these isotopes? So this would be the most abundant. What do you think would be the next most abundant? So most of the water was this. What do you think the next most abundant would be? H1, for sure. O17, I probably wouldn't go with that yet. I'd probably go still with O16 and H2. Or we could go H1, O17, or 17, remember, is kind of weird. It's not 17 that's the next, it's 18. H1, just based on the table. Which one of these two is more abundant? Okay, then what are the other ones? Well, we're out of time, so we'll look. You want to start thinking about that for tomorrow.